Hi, Dr. Mark here. Welcome to Let's Learn Computing. Today what we're going to do is take a look at asymptotic notation, otherwise known usually as BigO notation. And that's quite often used to help simplify time complexity functions when we're doing the analysis of algorithms, and also used to classify problems based upon the time complexity of the problem itself. Now, unfortunately, you may have been introduced to BigO notation kind of like this. All right, let's talk about BigO notation, which is one form of asymptotic notation. For a function on integers g of n, the function BigO of g of n produces a set. And that set is defined mathematically like this. So yes, the definition of BigO is quite simple mathematically. For a function on integers g of n, BigO of g of n is equal to the set of all functions f of n where there are constants c and n sub 0 such that 0 is less than or equal to f of n, which is less than or equal to c times g of n for all values of n greater than or equal to n sub 0. Simple, yes? Quite. All right, does anyone have questions? No? Seeing none. Thank you. We'll move on to our next set of theorems. We have 18 theorems that we're going to prove regarding order notation. So first of all, let's start with theorem 8.1, and we will begin with a very... All right, before our professor goes on and on and on with a bunch of theorems regarding BigO notation, let's just stop and sort of explain this, because that's really often where the things are lacking a little bit. There's nothing wrong with the definition. This is technically correct, but what we're saying is that, let's say, for instance, we have a function, f of n, is an element of BigO of g of n, or often we'll abuse the notation and write it this way: f of n is equal to the function BigO of g of n. Both of those are meant the same way. The one on the left is the proper way to do it, but all we're saying is that g of n here is a upper limit on f of n here eventually. Okay, so some constant times the function g of n will always be greater than or equal to my function f of n for all values of n that are large enough. And that's the asymptotic part of that. Okay, now c and n sub 0 here are constants. We don't really care what those values actually are. All we need to know is that they exist. Okay? So let's make this concrete and look at a particular example, an instrumented bubble sort. Here's some instrumented bubble sort code that you'll find in the Git archive for Let's Learn Computing. And so basically what we've done is we've taken the optimized bubble sort algorithm that repeats its process as long as it's done work. Whenever it doesn't have to swap any values in a bubble sort, it's done, and so it detects that and it quits early. The classical bubble sort would not do that, would just plow straight ahead with its algorithm until it's done, bubbled every element to the end. In any case, what this one has been modified to do is count the number of operations that are made in the process of the algorithm. And so what we're trying to do is roughly count the number of C++ operations that are executed during the process and report those back. It's not particularly important if we miss one or two due to the nature of BigO, as we'll talk about later, but this is pretty close. And so then what we can do is we can run this program for a variety of array sizes in the best, worst, and average case. The best case would be when the array is already sorted. Basically, bubble sort in that situation would just do a linear pass through the array and determine that it's already sorted and be done. Worst case would be something that's in reverse sorted order. That would require the maximum number of operations to accomplish. And then the average situation is just an array that's randomly permuted in any old order. So the code here is instrumented to do that in a variety of different array sizes for a certain number of tests. And it aggregates those values together and prints out the average number of operations for that size, given the best, worst, or average case. And so we can take a look at those number of operations graphically. And here's our first image here of the best, worst, and average. And again, what these lines represent is the number of operations taken is on the y-axis, and the number of array elements is on the x-axis. Red is the worst case scenario, average case is the blue, and the best case you can't really even see here because it's down below. Now, what we would expect is we would expect our best case time complexity for this bubble sort to be linear, big O of n, and we would expect our worst case time complexity to be big O of n squared. So let's take a look at just the worst and just the best compared to some values of n multiplied, or n squared multiplied by a constant, and see what we get. So here's our best case curve. This is the curve that we couldn't see on the previous diagram. This was the green line that was at the bottom. But notice that it's linear, very nicely linear. And then this is just actual linear values plotted. This is just n. Okay, so this is the number of operations. This is n. And if this best case is big O of n, we should be able to find a constant that brings this red line above the blue line eventually. So this is just n. This is 2n. Notice how this gets closer to the curve. 3n is right on top of it, and 4n is always above it. And so from that, we can be confident that our best case time complexity for this bubble sort is, in fact, big O of n. In the worst case situation, here's my worst case line, the blue line. And this is, again, the number of operations. The red is just n squared, where n is the array size in this situation. Just like before, if we want to prove or convince ourselves that the worst case for bubble sort is big O of n squared, we want to find a constant we can multiply this red line by to bring it above the blue line. So there's 2, 3, 4 is not quite there, 5 is right on it, and 6 is above it. So since there is a constant that brings n squared above the number of operations for particular size n here of the bubble sort, we can say with confidence that bubble sort, in the worst case, is big O of n squared. Again, before we sum everything up here in a moment, just want to make sure that this is just illustrating how big O is sort of an upper limit on a function that we're trying to simplify or classify. And in practice, we don't care about those constants at all, the c, the multiplier, or the n sub 0. We just need to know that they exist. All right, so let's sum everything up here a little bit. For our bubble sort algorithm that we looked at, when we instrumented it, we found out that the time complexity in the best case, b of n, is big O of n. And that was true because we can take the function n, that would be g of n in our definition here, multiply it by a constant, and have it be always above the number of operations taken in the best case by the bubble sort. Likewise, we can find the worst case time complexity for bubble sort was big O of n squared. In that situation, g of n is n squared, f of n is the number of operations taken in the worst case by the bubble sort, and we found that there was a constant we could multiply n squared by to put it above the number of operations taken by the bubble sort. Now, if we have a function already, let's suppose that we have a function, time complexity function, that looks something like this, right? An easy way to find out what the big O notation for that is is to pay attention to only the fastest growing term in the function, this one here, and ignore everything else, including constants. And so we would find that that would be big O of n, because the 13n is the fastest growing piece in that situation. Likewise, if we had a function that was like this, 3n squared plus 17n plus, I don't know, 35,000 or something like that, we would do the same thing. We would look for the fastest growing term in the equation, right, which in this situation is the 3n squared, ignore everything else, including constants, and all we're left with is n squared. And so that would be big O of n squared, and so on. All right? So big O is not so mysterious. It's just an upper limit on the behavior of a function or the growth of a function as our value of n grows large. Okay, so it puts sort of a cap on the behavior of a function. It gives us a way to classify it in the worst case. So hopefully that helps a little bit to understand big O. Thanks, and we'll see you next time.